everyone. Thank you for joining. So today, let's do the problem maximum depth of a binary tree. So we're given the root of a binary tree. We have to return its maximum depth. So a binary tree's maximum depth is the number of nodes along the longest path from the root node to the farthest leaf node. So our root node over here is 3, and our farthest leaf node is either 7 or 15. So our maximum depth is going to be 3. Or 3 in this way. So we're given our input, which is the root, and then our output is 3. So let's see how we can solve this problem. So initially, what I like to do is I would like to make a comment section and then try to explain this approach. So we have our input, which is given as the binary tree over here, which is 3, 9, 20, null, null, 15, 7, and our output over here is going to be 3. So identify the input and output is the first step, and then the next step is to see what the constraints are. So our constraints are going to be, the number of nodes is going to be from 0 to 10 to the 4, and our node value is going to be between -100 and 100. So those are our constraints. So that seems pretty reasonable. Okay, so now our next step would be to sort of diagram this out and then explain the approach. So while diagramming this, we first have to identify if we have any edge cases. So we see that one thing that we need to know that we have to check is whether the root is null. So if our root is null, then we have to return what are we returning? Yeah, if our root is null, then we are returning an empty array. So if root is null, then we return an empty array. Otherwise, what we're going to do is we're going to traverse down the tree and keep track of the count. So when we start, we're going to start at the root node, which is 1, and then we have 9 and 20. So this is how I'd like to draw my tree branches. So we have 9 here, and then we have 20 here, and then on the next step we have 15 and then 7. So when we start at the initial root node and we make a left recursive call and right recursive call, what we're doing is we're actually moving down the binary tree. And as we move down the binary tree, we will hit the point where we reach our leaf node, which is 15, 7, and as well as the 9 as well. The moment when we hit the leaf node, that is the point where we actually return something back. So when we hit a leaf node, what we do is we try to see. So here, let's look at this point. When we hit 15, we're going to have to return something. When we hit 7, we're also going to have to return something. Let's assume that when we return one count from each of these. So if we were to return 1 from here, and then if we were to return 1 from here, then that would mean we're just returning ones. It just means that we're returning a count of 1. So when we move up 1 call, that is the actual count that we're actually incrementing. So here, when we return 0, and then when we come back up, that one movement up, the recursive call is the actual count. So that movement would return a 1 call, and this movement up would return another 1 call. So here, when we return first, we would have to return a 0. Here, also a 0. And then when we move up, we return a 1. And so when we are moving up from here, from this side, we are moving up by 1, and the value that we would return over here would be 0. So we are going to take the maximum height from the left side and then maximum height from the right side, then find the maximum between those two, and then when we move up, we increment another count. So the maximum between the left branch, which is 0, and then the right branch, which is 1, is going to be 1. And then when we move up, we're going to have an increment of 1. So that is how we do the recursive calls and then increment the count as we move up. Now let's move back to the code in here. So how we would do this is initially we would have to like check our edge case. Our edge case over here is going to be if root is none, then we would just return 0. So our edge case, or let's just call it our base case in this case, we would return, yeah, this is edge case, or yeah, actually let's call this base case. Yeah, this is the base case. And then whenever we do the recursive call and we hit a leaf node, we return 0. And our recursive call is going to be as follows. We will return the maximum as we mentioned. So we're going to make a left recursive call. So let's do max depth. So here, this is our max depth. Let's do self dot max depth of root dot left and self dot root dot we do root dot left, and now let's do root dot right. So we're finding the maximum between the left and right. So whenever we hit 0, that 0 is being returned on these left recursive call and right recursive call at the point where we have our leaf node. So maximum between those two zeros is going to be 0. And then when we move back up, we would have to increment that by 1. So we are going to increment that by 1. So yeah, that would be our answer. And so let's test this out by running the code. There you go. We have the right answer, and the runtime complexity of this is the runtime for this is going to be 47. And yeah, so thanks so much for watching, and please like and subscribe.